is to demonstrate how to set up thermal fluid analysis for power conditioning unit in scSTREAM. First, let's open preprocessor and import CAD data. Preprocessor was launched. Then, initial wizard opened automatically. Let's set project name and working folder. Then, enable import CAD data and click next. Specify CAD data to import. The CAD data format is parallel in this demo, but scSTREAM supports most of the CAD data format, including native file of CAD software. You can see that the number of parts in this CAD data is over 2800. Click Finish to import CAD data and close Initial Wizard. CAD data import is completed. This simulation includes water flow in addition to airflow. Let's create a part to set domain for water flow. We will create this domain by utilizing existing parts, then extract volume to solve water flow. To set flow boundary condition, obstacle part is required, so we will cut the part to create obstacle part, then register the surface. Next step is to set computational domain. Double-click domain cuboid from left tree. Click Calculate Part Region to fit the domain to the entire size of the whole geometry. To solve airflow around the PCU, enable Extend Surrounding and input values. Click Preview and confirm the computational domain. Next step is to deactivate parts. Since this CAD data includes two versions of the simulation case, we need to deactivate some parts so that those are not included in this simulation. To deactivate a part, open Part dialog and enable Virtual Part. To deactivate multiple parts at once, select parts, right-click on them, select Change Part Setting Together, then enable Virtual Part. The next step is to set material property and heat source. There are multiple ways. In general, material property can be set by opening part dialog individually or using change part setting together menu by selecting multiple parts. Here we use simple input CSV file. No detail will be discussed here, but there is a way to obtain part list in CSV format and set the name of material property and heat source in Excel. For now, drag and drop material property files and simple input CSV file to draw window. You can see that material property and heat source is set. Now, let's open condition wizard. This simulation is expected to be laminar because Reynolds number is low. Also, radiation will be significant for components on the PCB because the contribution of convection is limited due to natural convection. Select laminar flow and check radiation. Click Next to set ambient temperature. Let's move to flow boundary to set flow boundary conditions. Set total pressure to Zmin and set static pressure to Zmax. For boundary conditions for secondary flow region, set flow rate to water inlet. And total pressure to water outlet. Click Next to move to wall boundary. Set free slip for to Xmin, Xmax, Ymin, and Ymax. Click Next to move to thermal boundary. Set open space radiation condition for all domain boundaries. Go to radiation from left tree. Click grouping region and set 1 for all domain boundaries. Go to analysis control. Select high speed forced convection and click update to use tuned solver parameters. Now we completed condition settings. Click finish to close condition wizard. We are ready to move on to meshing step now. Open mesh dialog. Select vertex detection type. In this demo, we set not to consider vertex detection by default. Instead, we will set vertex detection settings individually later. Input the standard length. Go to Parameter tab and create a mesh block inside of default mesh block. Then create another mesh block inside of second mesh block. In this dialog, there is a list of parts. We can set mesh settings for each part here Right-click water jacket part. Input number of divisions so that this part has the number of mesh divisions specified. Select multiple parts to set the vertex detection types. Please note that this setting can be set in simple input CSV file. After finish meshing settings, click gridding and meshing. Meshing took about 21 seconds with 8 threads, and the number of elements was over 93 million. After the meshing is completed, let's check the mesh. By hiding enclosure, you can see the mesh inside of the enclosure. From mesh showing mesh cross-section, you can visualize the mesh cross-section. You can select axis and move the slider to adjust the location of cross-section. You can interactively show or hide parts in tree to control what you want to see. Now, all the setup in preprocessor is completed. So let's move to solver by clicking the solver icon. Solver monitor was launched, and the simulation input file was loaded automatically. Click execute to run the simulation. Simulation completed. For your reference, the simulation takes 37 minutes using 96 parallels. Now, let's visualize the result in post-processor. Click post icon to open post-processor and load the result file automatically. Since this simulation is computationally expensive and result file size becomes large, it will take some time to load the data. Loading data is completed, and now you can visualize the result. For example, you can see the temperature by showing temperature on surface. Also, you can show the cross-section temperature, pressure, and velocity in plane. You can adjust the parameter to show vector to see the flow fields easily. With this, I will conclude my demonstration. Thank you for your attention.